So I'm Dan Coughlin. I'm the director of a program called QuakeFinder, joined here today by our CTO of the project, Tom Blyer, and Jim Lemon, who's our chief analyst in the group. So we appreciate the opportunity. Thank you to CITRIS and to UC Berkeley to provide this important forum and provide an overview of QuakeFinder. The picture you see here is from the most recent earthquake in Taiwan. Well, I'm not sure it was the most recent earthquake. The magnitude 6.4 that occurred earlier in the week, or late last week. Just as a teaser, we had sensors near this earthquake, and we've acquired the data, and we'll be using it in our analysis, and I'll go through that in more detail here. So QuakeFinder is it's a humanitarian R&D effort that's been sponsored by our parent company, a company called Stellar Solutions. This company is based in Palo Alto, California. It's an engineering services company. It's mostly systems engineering to the aerospace community, to the intelligence community, DoD, and some private companies like Lockheed and Boeing. About 140-person company, medium-sized systems engineering services company. And they have largely self-funded this R&D effort since 2000. Tom Blyer is the father of QuakeFinder. We've got a small and dedicated, passionate team that believe in this effort. So far, Stellar Solutions has funded this to the tune of around $25 million. We've enjoyed some sponsorship funding from NASA, from the Musk Foundation. PG&E is a good partner of ours, Vodafone and Telefonica in the countries where we have sensors. And we've been lucky to serve as the focal point for the kind of a growing international community of researchers and scientists that are looking at earthquakes from an electromagnetic standpoint. So most of my colleagues here are, when you think of earthquakes, you think of the mechanical motion of the Earth. We're looking at a much different signal as a potential precursor to earthquakes. And it's our mission to save lives by forecasting earthquakes. So most everyone here is familiar with the ecosystem of forecasting today. So on your left is the earthquake early warning system. This is a system that's been implemented in a few different countries. It's undergoing implementation in California and the Pacific. The object here is to measure the mechanical motion of the Earth as an earthquake is happening and provide adjacent communities, advanced warning up to the tune of 30 seconds, a minute, depending on how far you are away from the epicenter. It's been very successful in Mexico City and Japan. It's a great system, and that is, I think, it would be very beneficial to the state and the Pacific to save lives. On the far right, these are statistical forecasting models that, based on history of earthquakes in your region, it provides 30-year, 15-year probabilities of earthquakes and magnitudes, and those are largely used in earthquake preparedness and building codes. And then QuakeFinder. So it's an R&D effort to develop a technology and a system to enable a forecasting capability that will provide days or weeks of advance notice of an earthquake. To date, our theory is that we can see anything above about a magnitude 5, but that's still to be proven. Really quickly, I'm keeping an eye on the time here. So we focus on 3 signal sources. This is a complex chart, but on the right you'll see, so we have sensors. I'll show you on the next chart. We've got 165 sensors that have been self-funded, largely a grassroots effort to literally knocking on doors all up and down the San Andreas Fault, the Hayward Fault, and then 5 other countries to donate a portion of their property so that we can place our sensors in quiet areas, listening for using induction magnetometers, which is a fancy word for listening to slight changes in the magnetic field that could be generated by an electrical source in the Earth. And so we have magnetometers buried near our sensor suite that have battery and communication and other sensors. So we're listening for slight changes again in the electromagnetic spectrum. Second source is air conductivity. So this, the theory is, and what we've seen in past earthquakes, is ionization right at the ground level in the day or two, leading up to the earthquake. And then the third source is using an infrared signal by the GOES, our satellite. There's been cases in the past where there's an apparent, it looks like an apparent heating near the epicenter, future epicenter, and we look for that too. And so there's the slope change there. The QuakeFinder system. So I've got 5 minutes left. I'll go through this quickly. 125 sensors in California, about every 20 miles, every 10 miles rather. That is our theoretical range of our sensor suite, which is seen down the bottom left. It's hard to see in the scale, but it's basically this high. It's a self-contained unit. Our communication back to our data center in Palo Alto, California, is largely through a cell network. We've got some hardwire, we've got some satellite. And then, and we've been doing this, the sensors have been out since 2005. That was when the project really started deploying sensors in earnest. And we've got about probably 70 terabytes of data now. We collect these electromagnetic signals at 50 samples per second, very high frequency. And the stage of the project now, we have over 100, almost just shy of 120 earthquakes near our sensors in our data set, by which we are developing an algorithm to hopefully provide forecasting capability. Good. That is our plan. It's a research and development effort. We're not making claims of being able to forecast earthquakes yet, although we've seen some success. We've got international collaborators in Peru, Chile, Taiwan, Greece, and then Indonesia. And we are looking to continue to expand our sensor network. It's odd to say, but the more earthquakes that happen, it's better for us. We can build a statistical database by which we can develop these algorithms and hopefully prospective test and develop a statistical basis by which we can make earthquake forecasting. And in that regard, we're self-funded to really scale the system. We are talking actively with foundations, our government friends, and USGS, NASA, to ramp up the funding. We've got our eye on an operational state, hopefully within the next 5 years. And again, we work arm in arm with our friends at the USGS and other government agencies. And so we are working on algorithms. There have been some major advancements in signal processing in the past 10 years. We're employing those techniques to tease out these signals. And again, we see signals ramp up about 2 weeks before, kind of goes into a quiet period, and then again about a day before, which would be a nice little complement to the earthquake early warning system. And I think that's it. Yeah, and then this is kind of a feel-good, get off the stage chart. The potential benefits speak for themselves, and that is if we could provide 2 weeks to 2 days of notice, the tremendous preparedness that you could put in place, the emergency equipment, supplies you could potentially evacuate, and then you personally and your family could implement a plan in preparation. I think that's it. I made my 10 minutes. Good. Thank you.